Today we'll be looking at one-to-one functions. Our objectives will be to observe the relationship between functions, relations, and one-to-one functions, to define a one-to-one function formally, to examine the horizontal line test, and to calculate inverse functions. Let's begin with a review of functions. Remember I gave you the pyramid where we had dogs, labs, and black labs? And then we had relations, functions, and one-to-one functions. And I told you that the characteristics of the pyramid on the left are the same as they are on the right, meaning that a black lab has to also be a lab and also be a dog. It cannot bypass any of those categories and end up being a black lab. Well, the same is true with the pyramid on the right. Remember we had relations at the bottom. Some of them were functions. They were the ones that we played the function game with, and they passed that, or they passed the vertical line test. Today what we'll be looking at is what makes some of these functions be also one-to-one functions. So let's look first at the definition of a one-to-one function. A one-to-one function is a correspondence between the domain and the range such that each member of the domain corresponds to a different member of the range. I can show you best how this looks if we play the function game again. Let me remind you how the function game worked. On the left we had domain elements, and on the right we had range elements. And then we had a correspondence. In this case it was the color of car that they drove. Remember, if we played the function game, I would call out a domain element and you would respond with a range element. If you knew exactly what to respond with every time, then it is a function. So let's play the game. If I say Maria, you would respond with blue. If I said David, you would say red. But the minute I say Megan, you're not sure whether to respond with blue or green. When you hit that dilemma, you know that this is not a function. It's just a relation. Let's play the game again. This time, same domain, same range. Correspondence is a little different. It's still car color, but let's play the game. If I say Maria, you would say blue. If I say David, you say red. I say Megan, you say green. I say Jasmine, you say red. Every time I call out a domain element, you know exactly what to respond with the range. Therefore, this one is a function. Now let's take this one step further this time because we also want to know, is this a one-to-one function? And what the definition said was that each member of the domain would be paired with a different member of the range. Well, I want you to look at David and Jasmine. Both of them are paired with red. Another way to determine if a function is one-to-one would be this. If you can play the function game, can you also play it in reverse? Meaning that if I called out a range element, would you know which domain element you came from? So play the game, but let's play it backwards. If I called out blue, you would say Maria. If I called out green, you would say Megan. But when I call out red, you're not sure whether to respond with David or Jasmine. Therefore, this is not one-to-one. It's just a function. Let's play one more time. This time the domain consists of Maria, David, and Megan. The range consists of blue, green, and red. Before I can ask you if this is a one-to-one function, I have to ask you if it's a function, because it has to work its way up the pyramid. So let's start. Play the function game. I say Maria, you would say blue. I say David, you say red. I say Megan, you say green. If you know where to go every time, and in this case you do, then it is a function. Now the question is it a one-to-one function? Can we play the game backwards? If I say blue, you say Maria. I say green, you say Megan. I say red, you say David. Therefore, it is not only a function, it is also one-to-one. It is moved to the top of the pyramid. But there's another way we can determine if a function is one-to-one besides just playing the function game. We can also use the horizontal line test. Now you're familiar with the vertical line test, but this time we'll be looking at the horizontal line test. And it says this: a function is one-to-one if it is not possible to draw a horizontal line that intersects it more than once. I do need to make sure that you understand something though. The assumption here is that you're dealing with a function to begin with, which means by the time you're applying the horizontal line test, you have already applied the vertical line test to determine if it was a function. Let's see how this works. Let me give you this graph and ask you the question, is it one-to-one? Well, your first step would be to see if it is a function, which means you would apply the vertical line test. Well, there's a vertical line. It touches in one place. This time I'm simply going to draw one, but let me ask you, is there any other place that I could draw a vertical line that would touch that blue graph in more than one place? And the answer is no, there's not. So it is a function, and the reason for that is that it passes the vertical line test. Let me get rid of our vertical line now, because once we know it's a function, our next question is it one-to-one? This time we'll perform the horizontal line test. Let me ask you, how many places does my red horizontal line touch the blue graph? Well, only in one. What if I moved the red line higher? Would it still only touch once? Yes, it would. What if I moved it down lower? Well, it would still only touch one time. Therefore, this function is one-to-one because it also passes the horizontal line test. It is not sufficient to tell me that it passes the horizontal line test unless you've already done the vertical line test. Let's take another graph now, and I'll ask you the same question. Is it one-to-one? Well, the first thing you would need to do to determine that would be to do the vertical line test. Let me ask you, is it a function? Hopefully you remember, the minute that vertical line touches the blue graph in more than one place, this one is not even a function. Therefore, it cannot possibly be one-to-one. It cannot go to the top level of the pyramid unless it could go to the middle level, and this one cannot. By the way, just for curiosity's sake, what is this? Simply a relation. Now, one of the key factors about one-to-one functions is that if a function is one-to-one, it has an inverse, and we can calculate it. So let's talk now about an inverse function. Our steps for calculating the inverse of a function are as follows. First of all, we'll replace f of x with y. We'll interchange the x and y, which means literally everywhere you have an x, you'll write a y, and everywhere you have a y, you'll write an x. Then we solve for y, and finally replace y with f inverse of x. And I need you to hear how I read this piece right here. F inverse of x. Remember, right here is f of x, and this says we have its inverse. So let's take a problem and see if we can calculate an inverse. What if I gave you f of x is equal to negative 3x plus 2? Now, before you could start to calculate an inverse, you would want to graph this, apply the vertical line test to determine if it's a function. It would be. You would then want to apply the horizontal line test to determine if it's one-to-one, and this one is. So now you can say, I know it has an inverse, I just need to find it. So let's go through the steps. The first thing it tells us to do is replace f of x with y, which simply means write a y everywhere I had an f of x. So y is equal to a negative 3x plus 2. The next step in calculating an inverse is to interchange x and y. Trade the letters, if you will. So what I'll have next is x is equal to negative 3y plus 2. Then we're told to solve for y. Well, remember, if I want to get that y by itself, I need to start undoing those things that have been done to it. So I'll start by subtracting 2 from both sides. So I now have x minus 2 is equal to a negative 3y. I still want to get y by itself because I'm solving for y. So I need to divide both sides by a negative 3. When I do, that gives me x minus 2 divided by a negative 3 is equal to, and on the right side, when I divide by negative 3, I just get y. And the last step says replace y with f inverse of x. And at the same time I do this, I'm going to turn it around so that it'll look like you're expecting an inverse function to look. And here's what it says. F inverse of x is equal to x minus 2 divided by negative 3. You have 4 steps to arrive at this inverse, and those same 4 steps should be done every time you're asked to calculate an inverse of a function. Now, I want to focus just for a minute, and I want to remind you of something we talked about a minute ago. Remember on the chart that I drew with the car color? You could work your way from the domain to the range and then find your way back. That's what an inverse does for you. Well, let's look at this and see if our inverse does that. What we're about to do is not part of calculating the inverse, but rather just making sure our inverse does work. What if I ask you to calculate f of 1? Now guys, that's a number I just picked out of thin air to try this with. So I'm going to calculate f of 1. When I do that, I'll plug in my 1 and I'll get negative 3 times 1 plus 2, which is negative 3 plus 2, and that's equal to a negative 1. Now let me pause here for just a minute and make sure you understand the concept that's going on. The function f pairs a domain element of 1 with a range element of negative 1. If this were our diagram a minute ago, it would have been 1 paired with negative 1. If indeed our inverse function works, it should take a negative 1 and pair it back with a 1 so that we can find our way back as well. So what I want to do is I want to take this inverse function down here and I want to plug in a negative 1 and see if we indeed work our way back. When we plug in a negative 1, we'll get negative 1 minus 2 divided by negative 3. That gives us negative 3 divided by negative 3 for a final answer of 1. Notice our function took us from a 1 and paired us with a negative 1. Its inverse function took us from a negative 1 and paired it back to the 1. So it does indeed complete that cycle of taking us from 1 to negative 1, and then the inverse takes you back. Let's calculate an inverse for another function. I'll put the steps on the screen again so that you can see them. And this time let's use the function f of x is equal to x cubed. Replace the f of x with the y and we get y is equal to x cubed. Interchange the letters, so x is equal to y cubed, and then we want to solve for y. Well, this y has been cubed, so to undo that, I'll need to take a cube root. So I'll take the cube root of both sides, and what that leaves me with is the cube root of x on this side, but the cube root of y cubed is just y. Let me remind you, if you had the cube root of y cubed, that is just y. Let's rewrite that using our inverse function notation, and I get f inverse of x is equal to the cube root of x. Now, once we've done this step, our inverse is complete. Let's just check to see if it works. Let's take our original function up here, and let's just pick a number. I happen to pick 4 to plug in. That would mean that f of 4 is equal to 4 cubed, which is 64. That says that it pairs a domain element of 4 with a range element of 64. Let me come up here one more time. The function pairs these two numbers together. Well, to see if the inverse works, I would want to plug in the 64, and the inverse function is the cube root of x. So that's f inverse of 64 is equal to the cube root of 64. You could grab your calculator to do this piece right here if you needed to, but it turns out that it is indeed a 4. And what that tells us is that the inverse function pairs a 64 with a 4. On our diagram, it says it takes us back. Now, some of you are going to get a little wise here and say, well, I could have done this without going through all of these steps. If y is equal to x cubed, then to undo that, I would take the cube root of x. And I understand that some of you may see that, but they're not always that easy. So let's continue. What if I gave you this function? Now, even those of you who were thinking you had it figured out probably would have to pause at this one for a minute and go, I'm really not sure. So let's go through the steps. Our first step is to replace f of x with y. So we have y is equal to 2x plus 1 divided by x minus 1. Our next step would be to interchange the letters. Everywhere I have a y, I write an x, and everywhere I have an x, I write a y. The next step is to solve for y, and this one's a little hairier than any we've done before, so I do want to take you through these steps. To solve for y, we would begin by clearing fractions, which means we would multiply both sides by y minus 1. When I do that, it would give me x times y minus 1 on the left side, and on the right side, the y minus 1's would cancel, and I would be left with 2y plus 1. I want you to think of it like this. So on the left you see the x times y minus 1. On the right hand side, notice these would cancel, and that's where you get your 2y plus 1. The next step for doing this would be to distribute. That would give you xy minus x. Now the thing I need you to focus on this time that's different than anything we've done before is this. I'm solving for y, but I have a y here and I have a y here. In order to solve for y, I need to gather those on the same side of the equation and then factor out a y. Let me go through those steps with you. I'm going to subtract 2y from both sides, and I'm also going to add x to both sides. You may need to do that in two separate steps, but if you do, here's the line you would arrive at. xy minus 2y is equal to x plus 1. This is where we factor out the y. Remember how we can pull out a common factor if one exists? Well, this time it happens to be a y. So that leaves us with y times x minus 2 is equal to x plus 1. If we want to solve for y, this y has been multiplied by x minus 2. So we want to divide both sides by x minus 2. That'll leave us with y on this side and x plus 1 divided by x minus 2 on the other side. Once we have the inverse, we need to write it in such a way that anyone who came along after us would realize it is an inverse. So we write f inverse of x is equal to x plus 1 divided by x minus 2. Our inverse is complete at this point, but I do want to check and see whether or not our inverse would work. Let's take our original function, this one right here, and I want to start by plugging in a number that I picked. It happens to be a 2. When I plug in a 2, I get 2 times 2 plus 1 divided by 2 minus 1. That simplifies to 4 plus 1 divided by 1, or just a 5. Let me remind you, that says that the function pairs a 2 in the domain with a 5 in the range. Let's see what our inverse function does. I'm going to start with the 5, and we're hoping it's going to take us back to a 2. Let's verify whether or not it does. When I plug in the 5, I get 5 plus 1 divided by 5 minus 2. That gives me 6 divided by 3, which is a 2. Now let me remind you, the function took a 2 and paired it with a 5. The inverse function took a 5 and paired it back with a 2. So I do indeed know that this is the function and this is its inverse. Remember, this is only possible if you already know that this is a function, and we know that because of its name, f of x. You could graph it to see if it is one-to-one by doing the horizontal line test, and then and only then can you calculate an inverse, which we did right here. You may want to play with a few more of these just to get comfortable with that concept. Let me leave you now with my thought for the day. The only way to have a friend is to be one. I'll see you again soon. Bye-bye.